halfway.
We're barely making it. We're barely holding on to schedule here. We'll make it.
I think you want to decide on the next.
Yeah.
20, 22, 24, 26, 28. We're too short.
Yeah. No, it's like I just 3 people because I have 51st round.
Oh, okay. There we go. So we're at 30.
It was 31.
Oh, okay. You guys don't care though. You're here, right?
No, sometimes
You go back?
I like go back very regularly.
Really? You're like the 4 views that are out there?
all of them.
That's what I figured. Yeah. Okay. So last little bit of shear, and I do apologize. I put up a new set of skeleton notes, but I didn't get to it till this morning. But we're going to start deflections here in a second. But before we step away from shear and beams, okay, we talked about this idea, or started talking about this idea of shear flow on Friday, which is the concept of creating a composite section out of multiple other sections, other materials or different dimensions of the same material. Mentioned I-joists and wood construction, right? If you see house construction these days, a lot of times floor systems are made out of a wood I-joist, which is essentially, looks similar to something like this, but it's 2 different materials that are glued together, right? And we need to figure out what is that force that the glue has to handle, right? To make a composite section, to make it act like it's one continuous member. And so we started by looking at the definition of shear stress, right? Or the derived definition of shear stress that we have in flexure, which is VQ, this idea of VQ over IT, right? The shear demand at a cross section at some distance along the length times the first moment of the area. We talked about Q, right? Which is essentially the area above whatever horizontal plane we're trying to look at the shear stress at, divided by the moment of inertia times its thickness, which is essentially that same shear plane that we cut. What is the width of our cross section along that cut plane, right? And so from that, going back, we can figure out that shear, right, is essentially just the change in moment with respect to the distance along the length. So that's delta M over delta X. And then we have Q over IT. So then taking that and realizing, right, or going back to all the way back to like chapter 2 or 3, this idea that shear force is shear stress times area, right? Force is stress times an area, or stress is force over an area. And so if we set those, take our shear stress, plug it into our force, shear force equation, we get this equation here, right? VQ over IT times area. Well, the area in which that shear force acts is this horizontal plane area, which is delta X, which is our distance along the beam, times the width of our beam, or T. The T's cancel out here. So now we get our horizontal shear force is VQ over I times delta X, right, or distance along the length. Our shear flow which is a shear force per unit length, really is the force, horizontal force, divided by a unit length, right? So if we look at that, we take our delta X over to the other side, we get that our shear flow is VQ over I. Right? So total shear force right, which is our horizontal shear force, is really the shear flow times delta X, right? Or F sub H equals what we call Q times delta X, right? Shear flow, we're going to call Q. Right? So we know we have this horizontal shear force that's acting in our cross section at any given height, right? We can figure out how that shear flow is distributed along the length of our beam. And that's important because, right, we're fastening something along the length. Sometimes that fastening can be continuous, like with glue, but sometimes that fastening is discrete, right? We're making it at discrete points. For instance, here we've got this wood eye shape that's made out of 3 wood members, and those members are connected with nails, right? So then we have a nail that's probably at some sort of spacing, maybe it's 3 inches on center or something like that. So that's a discrete fastening at a given length or spacing. And so that fastener is going to have some sort of, or some amount of shear force, right, per fastener as we move along the lengths, right? So oftentimes, determine fastener spacing, call this S, based on shear flow requirements. This is typically specified as, say, some length on center, right? So it'd be, for example, 6 inches on center, 6 millimeters on center, so on and so forth, 1 foot on center. So we can figure out the force per fastener really equal to the shear flow times the spacing, right? Shear flow is a force per length, right? It kips per inch, pounds per inch, newtons per millimeter, and then we would have some sort of spacing to our fasteners, nails or bolts, multiply our shear flow by that fastener spacing, we would get how much force we need to carry in each one of these nails. So if we look at demand, right, ultimately in design, we always want the demand to be less than or equal to capacity. So our demand is that horizontal shear force, right, which we now know, or force per fastener, would be the shear flow times the spacing. Well, that better be less than or equal to our capacity. Call this NF times VF, or NF equals number of fasteners VF equals allowable force per fastener This is in shear, right? Fasteners are going to have different capacities based on the loading type, whether they're in tension, compression, or shear. This would be our shear stress tau F times the area, right? This is our fastener areas. This is our allowable stress. Whew, just got it in there at the corner there. So we can figure out a demand based on the shear flow. That shear flow is coming from the demand on the cross section, right? The shear that's acting at that specific point, as well as the first moment of the area of the material that's beyond our fastened location, right? So if we looked at our cross sections here, right, if we were looking at nail A, we'd really be looking at Q of the flange, right? That amount of material that's beyond our plane, right there. If we started looking at some of these other ones, we might look at the material beyond our nails. Here we might be looking at, right, the material beyond the nails, figuring out what Q is. Which this is not right. This should be this. Okay.
So lowercase q is the shear flow. What is
Capital Q is the first moment of the area. That's our YA. Or summation YA if you split it up into multiple segments. All right, let's do an example here real quick about shear flow and fasteners. Okay. All right, so imagine we have a T-style cross-section. It's made up of two pieces of the same material, okay? The flange, or that top section of this T, is attached to the lower stem section of this T with bolts, right? Lag bolts, in particular here, okay? The cross-section, or the total element, right, beam element, looks like this. It's got a span of 7 feet, and then it's got a cantilever beyond that 7 feet of an additional 7 feet, and that cantilever has a point load on the end of it of 500 pounds. Okay. Spacing, right? S. S we're going to be given as 5 inches. So we're going to space our bolts out along the length of this entire member at 5 inches on center. That's going to attach our top flange to the stem of this T section. Well, we know that the shear force, or the force in each fastener, is our shear flow times the spacing. We know our spacing is 5 inches, right? I'm giving you that. Our shear flow is this VQ over I. Well, if we look at I, for instance, for this cross-section, that gave us the neutral axis of this cross-section. We need to figure out what the moment of inertia is. Well, we would use the Parallaxis Theorem, right? AD squared plus I for each of these two cross sections, right? We would do it for the T section, or the stem of the T, and then the flange of the T. Right, this would be, say, Y bar 1. Y bar 2. For our block 2, we could do I for a rectangle we know is BH cubed over 12. So we would figure out what our moment of inertia is for each of our individual blocks. We would know the centroid, right? They gave it to us. If we didn't have it, we could figure it out, right? Y bar, summation Y bar A over summation A, right? Find our centroid. If we didn't have our centroid, they gave it to us. So now it's easier, one step closer. Essentially use the Parallaxis Theorem. We know that the moment of inertia of each individual block about its centroid is BH cubed over 12. We would add to that this parallel axis component, right? The area times the distance between the centroid of our individual component and the centroid of the overall component squared. We would add all that up, and based on that, I'm not going to go through all that. We would get a moment of inertia of 290.7 inches to the fourth, hopefully. So that's our moment of inertia. Now we need to know, well, what's our shear force, right? Our shear force is going to affect our shear flow. Obviously, if we maximize our shear force, we're going to maximize our shear flow. And we really are looking for the shear force in each of the fasteners. So we really want to know what the maximum force is in each of our fasteners. So we are going to do a free body diagram. We're going to have some reactions. I'm going to guess the directions of these reactions. Right, at point C, we got external force, 500 pounds. We know that this is 7 feet and this is 7 feet. I'm going to say this is positive X, this is positive Y. We have 3 equations of equilibrium and we have 2 unknowns. This is a determinant, right? We can figure out what our reactions are, or unknowns, forces are. I'm going to do that first by summing moments about B, setting that equal to 0. I did sum the moments about B because it gets rid of the reaction at B. And I can just calculate directly what, I'm going to calculate directly what the reaction at A is. So if we set that equal to 0, right-hand rule, 500 pounds times 7 feet, force times moment arm. It's negative, right-hand rule, right? Thumb's pointing into the page. Plus we've got this reaction times 7 feet. I assumed a direction for the reaction. You could have assumed the other direction. But I assumed it was the reaction A is going to be downward. Using that, a moment about point B, we get a positive RA times 7. Essentially results in 500 pounds equaling R sub A. If we sum forces in the Y direction, that's our second equation. We have negative 500 pounds minus R sub A, right? Assuming it's acting downward, plus R sub B, assuming it's acting upward, we get R sub B equal to 1,000 pounds. Make sense? Right. Our summing the moments about B equation came out with a positive answer for R sub A. It's essentially reaffirming that R sub A was indeed in the direction that I assumed. And then summing forces in the Y, using those directions, we get a reaction at B at 1,000 pounds. So we want to know what the shear force is. Well, the shear force requires us to develop a shear force diagram based on the rules. We're going to get something like this, right? Shear force diagram only changes when we have an external applied load. Our reaction is an external applied load. It's a discrete reaction, right? Point load. So it creates a vertical jump in our shear force. And we have no more applied loads until we get to the support at B. And we have this reaction we just calculated is 1,000 pounds. We bump back up in the direction of the applied load, which was upward of 1,000 pounds. So we go bump across the axis, we get to positive 500 until we run over to where the actual applied load is at, negative 500. We drop back down to 0. Right. This is our shear force diagram. Therefore, shear is plus or minus 500 pounds maximum, right? Those are our maximum shear forces in our cross-section. Well, so now we have V, we have I. We need this first moment of area, right? Q, summation Y sub I, A sub I. Talked about that back here, right? Essentially need to figure out that horizontal plane with which we're going to cut this cross-section at. When we cut this cross-section, we're going to figure out what is the distance to the centroid of that area that's beyond our cut, and then multiply that by the area beyond that cut, right? So y times a. In this case, our y, right, we're going to be looking at the intersection between these two pieces. And the intersection between these two pieces is at that surface right there. So the area we're looking at is everything in green, and then we're going to want to know where's the centroid of that green area with respect to the centroid, right? The actual centroid of the whole area. So if we do that, right, if we're 3.5 inches down to the centroid to the top of this green area, 1 inch is the centroid of the green area, we're at 2.5 inches. The area of that green area is 2 inches deep, 8 inches wide, 2 times 8. So we're going to say 2.5, that's our y. Area is now 2 times 8. Right, this is area. We get 40 inches cubed. Okay. So our horizontal force is S really times our shear flow, which is this VQ over I. So we get plus or minus, right? Because our shear force of 500 pounds can be in both directions, times 40 inches to the third, that's our Q, all over 290.7 inches to the fourth, that's our I. Our spacing is 5 inches. We get 343 pounds per bolt or fastener lag. Any questions? You're calculating something that is connected like this, right? We're really trying to figure out an entire shear force, right? That's acting through this element and transferring it to other elements. So when we're looking at Q for this type of situation, right, we're going to look at Q for this pink or I guess magenta highlighted box, right? We're not going to be looking at the entire. We just want to look at what's the area that needs to be transferred across these planes. So it would be the Q would be Y to this purple box, right? And the area of that purple box. And not the entire thing. Okay. I posted homework out on D2L right before this. It's going to be due Saturday at midnight, and the reason why I did that is the quiz, okay, over this material is also going to be available on Saturday, but Saturday at noon, and it's not going to be due until Tuesday at midnight, okay? Just essentially pushing it out so that, one, you've got enough time to do the homework, and then two, that the homework gets turned in early enough that you have enough time for the quiz after the homework, right? So you'll have a solution for the homework. Okay. Oh, shit. You know what I did do? Damn it. This might take a second. Take my time here. Should be. Connected. Boom. Did it. Not fast enough? Too fast? Slow down. Okay, so we're done with beam bending. with respect to stresses, normal stresses due to moments, shear stresses due to shear forces, and we're going to jump into deflections. Deflections is all in chapter 10 of the text, okay? All right, chapter 8 and chapter 9 all relate to stresses. All right, really all about life safety. Should really amounts to strength. Right. And all of the stuff that we've done in chapter 8 and 9 with respect to bending, right? Chapter 8 was bending. Chapter 9 was shear. Right, we were calculating stresses based on applied forces. And based on all the stuff that we've learned previous, right? We already had gone through shear stresses. We've already gone through normal stresses. The concept of, factors of safety, design parameters of allowable stresses, right? And how we would select materials or select geometry in order to make sure that our capacity is greater than demand, right? That's ultimately what we're always shooting for, is that our capacity is greater than demand. That'd be a life safety issue. Well, now we're doing deflection. Deflection is normally not a life safety. It is a major design component for usability. It's basically to ensure proper function of systems. For you civil guys and gals, right? Building vibrations. What is going on here? I can't write. Vibrations or movement. So I've mentioned in the past, like ponding of roof systems. If it rains, the roof deflects. If the roof deflects, it no longer sheds water, say to the outside edges, scuppers or something, right? Those are those little discharges you see on the sides of walls and buildings, right? So if the scupper then becomes at a higher elevation than your deflected roof system, you're going to create a pond. Well, the pond brings more water to the center of your roof system, which makes the deflection worse, and it just exacerbates itself. It just goes on top of each other, right? You don't want that. Right? So deflections are not a good thing. Not a very usable building when it does that. On the mechanical side of things, you guys, when we're talking about gears and bearings, all the cool shit. Tolerance has become a big issue, right? Things deflect too much. The backlash between gears can be too much. It starts wearing the gears out prematurely, or they're no longer effective to even transfer loading, right? Bearings, same thing, heat up, explode. So deflection can be a big thing, right? Proper function of the system. It all comes down to really serviceability. Concerns, right? It might be safe, but is it usable? Right. So when we talk about deflections and beams, okay, we can start by looking at some of the coordinate systems. usually is X is off to the right, Y is up vertical, and Z is out of the page. Right, when we've been calculating our moment of inertia, we've been calculating it based on, wow, that's definitely not a rectangle, huh? Getting a little loose with my drawing. Right, remember we called this our neutral axis, which in this case would be this Z-axis if we were looking at a section. This would be our Y coordinate, vertical. Right, now it would be our centroid of our cross-section. Right cross-section here, so this makes sense. Cross-section. So as I mentioned, X is positive to the right. So if we were looking at dx, right, a small amount of length along our member, right, this would be our small length. We will be doing integrals, which really is not cool. But we'll get through it, I promise. Right. Y, right, is our vertical axis, which really gives us the ability to describe our location within a cross section. Right, where are we at? We're doing this with normal stress and beams due to bending, right? Negative my over I, locating ourselves within the cross section vertically. Then we have this V, right? This is what we call our deflection coordinate. And this is really relating to what is the deflection of our neutral axis, right? So as we look at our beam, and we analyze it based on externally applied forces, right? We've got maybe an external moment, concentrated point load, uniform load of varying degree, right? Acting on this beam. This beam deflects because of these externally applied forces. Right? We get this deflection of our neutral axis. It would move in the Y coordinate system, right? An amount that would be considered V, right? What's the end game here? End game. We want to relate behavior of beam based on geometry and loading, right? Which is what we've done up to date in this entire class, right? We're going to relate what the behavior is. For the most part, we've been relating stresses, figuring out what stresses are based on our geometry and our applied loads. Well, now we're going to figure out deflection based on geometry and applied loads. So if we look at our point load at midspan of a simply supported beam, okay, we have P acting at midspan. We'd have P over 2 over reactions. We draw a free body diagram. We figure out our reactions based on the span length, right, and our applied loads. Based on that, we could then develop our shear diagram. Then we could figure out our moment diagram. Well, then from our moment diagram, we can actually figure out what our slope is. Right? What does that deflected shape look like of our beam under its applied loads? And based on that slope we can then figure out, well, what's the deflection of this point load at the midspan of a simply supported beam, right? And they're all interconnected, right? So if we look at deflection, right, this is V. Deflection equals V. Our slope is really equal to the change in deflection over the length, right? Really looking at this diagram, I mean, essentially, it's 0 in the center, right? Our slope of our deflected shape is 0. We're not going up or down in deflection right at the very bottom. So it's the change in deflection as we move along the length. Then we have moment M. Now we start getting into material and geometric properties, right? EI, modulus of elasticity, and moment of inertia. Well, that's the second derivative of deflection with respect to distance along the length, or essentially it's the derivative of the slope line. So to get from deflection to slope, we take the derivative. To get from slope to moment, we take the derivative. If we want to go to shear, anyone guess what we do? No takers. Take the derivative. One more time. And this is for constant values of EI, right? If the modulus of elasticity or the moment of inertia changes along this length, it throws everything out the window, right? Because we're going to be changing a lot of how the beam behaves as we go along the length. We're changing our stiffness. We're changing our stiffness with respect to geometry or material, is really the EI, right? Modulus of elasticity, E, is the stiffness of just the material, right? Our stress strain diagram we talked about early on. And then the moment of inertia, as you guys knew in 203 and how we've worked it through in 208 here, right? It's essentially the stiffness or resistance to rotation of the cross section. So the EI is stiffness based, so it has to be constant throughout the length. Finally, we have, right, load. We went to shear. Well, then there's this load that we have acting. Load, in this case, call it W. EI. Any guesses what it is? Seriously? Oh God, thank God. I thought I had lost you all for a while there. I was up here all by myself. The fourth derivative of deflection with respect to the distance along the length times EI is the load. This little guy right here is the fourth order differential equation for beam bending. Now you guys all have something to flex on. What did you do in class today? Well, I figured out the fourth order differential equation for beam bending. That's it right there. I'm going to derive this shit, okay? And it's going to make even less sense, probably. Call slope theta. And there's a connection here, which we're going to derive. That connection is based on this idea of a radius of curvature that we already talked about, right? Rho. So how do we get from, I think it's fairly easy to say, if we knew that we had a deflected shape, the slope is just that, right? The slope of our deflected shape, okay? So we go from deflection to slope. The derivative, definition of derivative is slope of a line, right? Change in something over a length, right? And so these, to get from deflection to slope, not too bad. You go from slope to moment though, right? How do we make that connection between, whoa, y, EI, second derivative of deflection with respect to x, why does that equal the moment? This is when you guys fall asleep and I get excited, okay? Well, let's start by saying from chapter 8, everybody remembers our favorite chapter 8. We derive this equality, right? Radius of curvature, 1 over the radius of curvature equals k, which equals m over EI, right? And it's this portion that we're going to be interested in right here, right? 1 over the radius of curvature is the moment, the applied moment over EI, right? So if we looked at a beam with a couple different radius of curvatures which have to do with our applied moments, we looked at, if we had a positive moment, we have a positive radius of curvature. If we have a negative moment, right, frown has a negative radius of curvature because the distance to the origin, right, of a circle that has this curvature to it is below the beam when you have a negative moment and it's above the beam when you have a positive moment. So positive radius of curvature, negative radius of curvature, right? Positive m, positive radius of curvature, negative m, negative radius of curvature. Right? So let's look at a cantilever. All right? So we looked at a member, beam member that was fixed at its end, right? A diving board. And we looked at a diving board and we allowed it to displace upward, okay? Someone just jumped off of it and we took a snapshot of it as it rebounded up, okay? And it had some amount of displacement, okay? So if we look at a cantilever, if it's displaced upward, right, it's deflecting into this smiley face. If we were to cut a section of this, right, there's going to be a positive moment in this member, right? Compression on the top, tension in the bottom. So we have a positive moment. Well, we just know that we get a positive radius of curvature. This radius of curvature is positive, right? And we look at a small portion of this diving board between points A and B. We're just going to look at some small portion of this diving board from point A to B. This small portion of diving board from A to B is going to have a length ds. That's what we're going to call it, ds. Right? And that ds, right, from point A to point B, A's got a radius, B's got a radius. The distance between those two radii is this change in theta, right, d theta. And the length over d theta is ds. So now let's blow this thing up so you really don't know what's going on. Now, hopefully you're following a little bit, okay? So if we blow this up and get a better look at it, all right? ds, or this small length along our diving board, right, is really equal to the radius of curvature times our change in theta, right? So rho d theta, right? That gives us arc length. The radius times your angle is your arc length. if we're looking at a very small theta, ds, we're going to say, is equal to dx. As d theta gets super, super small, right? Really, 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 really small. The length of ds is essentially going to be dx, right? That's all I'm saying, is that if we're looking at a very, very small length of this diving board, okay, the length of that diving board is essentially the horizontal length. And so if we say that, if ds equal to dx, we can plug dx into here, and then we get dx equal to rho d theta, which essentially says now we could rearrange this and say 1 over the radius of curvature is d theta over dx, right? We'll look at that. We got this equality up here, right? 1 over radius of curvature. We have a relationship of 1 over the radius of curvature equals the moment divided by EI, which is essentially saying now d theta over dx is the moment over EI. Not there yet. We're getting there. It's one part of it. Okay. So just based on geometry, we can come up with this relationship between the moment and the change in theta over the length. Right? It's essentially the slope. So if we start looking at rise over the run, essentially the slope as we go across this length of dx. Well, the slope, or the rise over the run, knowing that this vertical component is this vertical component is deflection, right? dV, okay? Right? That's the change in the height of our diving board as we go from one end to the other. At any given point, our deflection is dV. And so if we're looking at a small section of this diving board, the change in our deflection is this dV. So that would be our rise. So if we're looking rise over run over dx, it's really dV. Well, over the run, well, that's just the run, which is dx, right? That's the distance we're looking over. So the slope as we go from A to B is going to be the rise over the run. So dV over dx. Well, dV over dx is the same as saying the opposite over adjacent, right? Those are the lengths that we're really taking out of here, dV over dx. So that is opposite over adjacent. Well, the tangent of theta equals the opposite over adjacent. Theta being this angle that we have, this displaced diving board. And we know at small thetas, the tangent of theta is really just theta. So we end up with, therefore, dV dx is no longer tan theta, but it's just theta. We're looking at a very small portion of this beam. If we take the derivative of this, we get d theta dx equals the derivative d dx of the deflection dV over dx, which essentially, damn, you're so close. Bet you guys want to hang out, don't you? Watch it. Take that as a no. We'll finish this on Wednesday. Don't forget,